Hi, Assalamualaikum and good day. Today we will continue on another method of controller tuning, which is online controller tuning. Okay, there are several methods of online tuning. The first method is called continuous cycling method. Okay, few steps are involved as follows. Okay, first, step 1, we set the derivative time tau d to 0 and integral time tau I to the largest possible value. Okay. Second, we need to set KC value to a small value, for example 0.5, and then set the controller to automatic mode. Okay. Third, introduce a small set point change so that the control variable move away from the set point. Then increase KC values gradually until a continuous cycling occurs or until a sustained oscillation is obtained. Okay, now the numerical values of Kc that produce sustained oscillation is called the ultimate gain, Kcu, and the period at this Kc values is called ultimate period. Okay, next, calculate the PID setting using Ziegler-Nichols tuning relation given in table 12.6. And last but not least, evaluate this controller setting by introducing a small set point change and observe the response. Fine-tune the setting if necessary. Okay, this method is actually used in your lab 4, but due to the malfunction of this equipment, you cannot operate this method. So these are the common responses of continuous cycling method. Now, can you spot the response with sustained oscillation or continuous cycling? Part A, B, C, and D. Which one? Okay, the sustained oscillation is shown in figure 12.12b, which produce the same amplitude. Okay, so as you can see, the period here, okay, from here to here is your period. So the period here is called ultimate period, and the Kc value that produce this sustained oscillation is called ultimate gain or Kcu. This is the tuning relation given by Ziegler-Nichols that need to be used for continuous cycling method in step 4. Another method that can be used in online tuning is a step test method. Okay, unlike a continuous cycling method that is time consuming, this method is simpler, but both methods are proposed by Ziegler-Nichols. Okay, there are only 3 steps here. Okay, first, set the controller to manual mode once the process has reached steady state. Okay, second, introduce or apply a small step change in the controller output. And last but not least, calculate the controller setting based on the process ration curve of the open loop response. Okay. Now, can you tell me what's the difference between continuous cycling method and step test method? Okay. If you notice, okay, this method, step test method produce an open loop response, while the continuous cycling method produce a closed loop response. These are the typical process ration curve. Okay, the first figure show the response of non-self-regulating process, while the second figure shows the response of self-regulating process. So what's the difference between self-regulating and non-self-regulating process? Okay, self-regulating process is the process that can reach the new steady state value without the corrective action from the controller. So as you can see, this is the new steady state value because the response becomes steady, right? Okay, while the non-self-regulating process is the process that do not reach the new steady state value without the corrective action from the controller. So if you can see here, there is no steady state values achieved because the process is keep increasing with time, so the process is not steady. So there is no steady state value over here for non-self-regulating process, but both are without the corrective action from the controller because both are the response of the open loop process. Okay. So now, what's the information that can you obtain from process reaction curve? Okay, one, you can get the value of the time delay. So let's say for the second figure here, if you draw a tangent line at the inflection point, so this is the inflection point, you draw a tangent line, okay, the point here is the value of your time delay, and the point here is the value of tau plus time delay. So obviously if you know the value here, you can get what is the value of your time constant, and you can also find the value of your gain. You know that gain is the change of output over the change of input. So now this difference is the change of your output, and the change of the input usually given in the question. Okay, now let's take a look at this exercise 12.1. Okay, the following transfer function was obtained from the experimental step response data of a shell and tube heat exchanger system as follows. So this is the transfer function obtained from the step response data. Okay. Now, design a PI controller using Ziegler-Nichols setting. Okay, now, the first step is to consider the stability limit of 1 plus GOL equal to 0. So now substituting what is GOL. GOL is the multiplication of your G times GC by assuming G equal to GP, GV, and GM. Okay, so this is your G. Substitute in here. Okay, now okay, for GC, you substitute the value of a proportional controller transfer function, which is KC, and then so this is the first step, and then the second step is to use paid approximation for your time delay term, e to the power of negative 1.7x. So you substitute using the paid approximation expression. Substituting the paid approximation, rearranging the equation, and expanding, you get this equation. And now the third step is to substitute S with JW, J times omega U, and KC, you substitute with KCU. And bear in mind that J square is equal to negative 1. Okay, J square is like I square, the imaginary part. Okay. The next step is to separate between real and imaginary coefficient. So this one with J is the imaginary part, and the real part is without J. So this one is the real part, and equate it with 0. So you can calculate the KCU values and the omega ultimate angular frequency values. And finally, you can calculate the ultimate period, which is equal to 2 pi over angular frequency, because one cycle is 2 pi, so that's why you divide 2 pi with your frequency here to get the period. Okay, once you get the value of KCU and PU, you can directly use table 12.6 to calculate the PI controller setting, which is KC and tau I. So you get the value of your KC and tau I. Okay, that's all. Please don't forget to fill in the attendance form. Hope it will help for test 3 and assignment as well. Thank you.